Hey guys, welcome to our lunch and learn today. We've got about an hour to talk about noise, vibration, harshness. I'm Adam Robertson, worked with CarQuest Technical Institute for well, the better part of 2 decades now, and I recognize some of the names that are in there anyway. But Brenda, I think I'll take the opportunity before we get too far in. You brought up AT East; it's coming up, and guys, I'll be at AT East this year, of course, with one of our other instructors, Lonnie Horn. If you guys have never seen Lonnie present, he'll be presenting on Saturday. He's awesome instructor. You got to see what he has to say. As far as myself, I'll be presenting all day Friday. I have two different classes that we'll be doing live there. That is on leak sealing and detection strategies. It's an incredible class, lots of takeaways, and not just how to use the proper silicone or anaerobic compound or what seals to use, but a lot of tips and tricks on finding leaks and then properly sealing them. So I think you'll get a kick out of that. And then the other class I'm teaching on that Friday will be advanced network diagnostics. And I've got some really cool new technologies that I've been working on as far as developing diagnostic routines for communication networks. So I'm going to have a great time with that. But for today, Brenda, I'm going to take the screen over if you don't mind, and I'm going to jump into my program here. Brenda, would you let me know, can you see an absolute mess of my screen right now? Did it come through to everyone properly? It should have. Yeah, that's actually how my automotive brain works. So don't pay attention to all the waveforms on there. But as long as you guys can see it, that's all that really matters here. So off and running, guys. Once again, welcome to a noise, vibration, and harshness analysis. So what an incredible topic. And, before I go far, please remember, if you like what you see here today, or you're interested in any more training that CTI and myself have to put out, our website is ctionline.com. If you cruise over to that website, you can click on the virtual classroom and guide yourself through. And keep in mind, any day of the week, Monday through Thursday, we have online classes going on from a variety of different instructors. So there's really a lot of opportunities there if you're interested in it. But once again, that's ctionline.com. Now, I'll start this off with a small video that I have. We'll pull the noise away from this so you don't hear it. But wouldn't it be cool if all vibrations were really this easy to find? I mean, I think any of you sitting there looking at that video go by should be able to see that there's something really wrong with that Cummins harmonic balancer on the front and the bolts are loose. Things like that are not hard to find. However, guessing at noise vibrations can be costly. And I'm not going to sit here and read all this stuff to you, but I want you to think about where we've come from in the past. I've been working on cars for quite a long time, and I remember my style of learning how to find noises and vibrations. And well, we just called it seat of the pants diagnostics, really. And you had to learn, and it was a steep learning curve. I mean, gosh, you'd drive a car and you'd feel a vibration, and you'd grab the guy that's been doing it for a couple decades longer than you. He'd drive and go, "Oh, that's a bad U joint. Oh, that's a flag pulling drive line. You've got a tire that's out of balance. You've got a rear end bearing going out." And it was always so frustrating to have the old guys in the industry just drive it and tell you what's wrong. And so over the years, you learn, and you make some incredibly expensive mistakes, man. You rebuild a rear end on a car because you swore it had a bearing out of it, just to find out when you put it all back together, it was a bad tire that was making noise, not vibrating, not out of balance. So as you look at these different things that are on here, the process of elimination can be very, very expensive. So one of the answers we have for this is noise, vibration, and harshness. Now, I want you to think about the basics, and I mean just the nitty-gritty basics of noises and vibrations. First of all, guys, when I speak about noises and vibrations, they're really the same thing to me. Now, think about it. Any noise you hear, heck, my voice that you hear right now is a vibration. Any vibration you feel is a noise. Now, granted, you may not be able to audibly hear that vibration, or you may not be able to audibly hear that noise. The thing is, they still work on basically the same spectrum. And whether you're hearing it or feeling it, we will approach diagnostics basically the same way. And the basics of the equipment available to us today is this. If I have a way to measure, and I put this in the upper left-hand corner of your screen, if I have the ability to measure the vibration or noise, and I'll call it vibrations from here on out, or heck, whatever I say, but if I have a way to measure it, What I'm looking to measure is the speed, or how many times per second is that vibration being produced? Is it being produced 12 times a second? Is it being produced 100 times a second? How many times per second is that noise being produced? Then I want to take this same measurement of how many times per second the vibration is being produced. And it would be nice in many cases if I knew which direction that vibration was coming from. Is that vibration going fore and aft in the car? Is it going vertically with the car? Is it going lateral in the car? Because some types of vibrations, knowing which direction it hits from, may also allow us to pinpoint where it's coming from. And then once I know how many times per second that vibration is happening, once I know the direction that that vibration is coming from, I need to be able to measure the harshness or the strength or how loud it is. So basically, I'm going to measure frequency, direction, and force. And then I added in another one here called order. We'll cover that in a little bit. All right. So frequency, order, direction, and force, the basics. So let's move on here. Why do we need to understand these items? On the screen in front of you, I have an NVH capture that I took off of a General Motors Generation 2 3800 V6. Probably one of the more common and gosh, guys, probably one of the best V6s ever produced, in my opinion. But I've got a Generation 2 3800. The story behind this vehicle goes like this. The customer destroyed the trans in it. And they need to have a new transmission put in. Once the transmission was installed in the car, the customer noticed a relatively violent vibration. Now, according to the customer, that vibration was never there before you did the work. Well, come on, man. As a technician, it's towed into your shop with a dead trans. You can't diagnose it till the trans was fixed. So transmission gets put in. The car is taken to the local dealership to have this vibration checked. The local dealership says, hey, you have a problem with the balance shaft in the engine. Now think about this. A Generation 2 3800 V6 is a very smooth running V6 when everything's all right. It's a counterbalanced engine, and they are just a great piece of equipment. So here it gets diagnosed at the dealership as needing a counterbalance diagnostics. That's tearing the whole engine down at this point. The customer wants to get a second of opinion. I got to tell you guys, this is one of the very first NVH captures that I was involved with when I was just learning this equipment. And it's probably one of those flagships that stuck out to me and said, I like this concept, because I hooked my NVH equipment up with the ability to measure the frequency, the order, the force, and direction. Now, in this case, I'm doing what we call a vector summing. So what I've done is I've taken the direction out of the equation, and I've just asked my software, hey, you know what? It's got an engine vibration. I don't really care which direction it is. I just want to see the vectored sum of the vibrations themselves. And then I ask the software to organize it into what we refer to as order. Now, I have a few different graphs on the screen. I have a massive graph right here saying 61 milligrams of force under a heading called E1. The E1 stands for engine order 1. The next block over is engine order 1.5, followed by engine order 2, engine order 3. The order is how many shakes, how many times that vibration happens per rotation of the component. So if I was looking at a rotating engine, for example, I've got the engine, it's rotating away. Then every time that crankshaft goes around, I'm going to call that an order 1. And so here's what happens. I have a massive amount of vibrations happening once every time the crankshaft revolves. There are a few vibrations over here, but what I'm feeling is I'm feeling what I refer to as an engine order 1 vibration with a massive amount of force. By just looking at this graph, I can tell you, guys, that can't be a balance shaft. No. If this were a balance shaft issue, and this is for another class further down the road, it would be showing a majority of the force under an order 3. But because all of my massive vibration is shaking, it is shaking once Every time the crankshaft goes around, every time the crank rotates, there's a shake, a shake, a shake with a massive amount of force. That tells me that the vibration I'm feeling in this engine most likely is something directly bolted to the crankshaft, whether that be on the harmonic balancer end, whether that be on the flex plate or flywheel end or the torque converter. But every time that crank goes around, it's got a shake, and a violent shake. So what it did to me is it led me to the direction to say, wait a minute, I'm not ready to pull this engine apart. I can't pull the engine apart because I need to take a look and see what's connected to that crankshaft that would vibrate once around. Well, just a little bit of brain work, a little bit of thought process, you realize that in the General Motors Gen 2 3800, they had the L36 RPO and the L67. The L67 was a supercharged version. You also realize this is an externally balanced crankshaft where they put a balance weight on the flex plate. And there is a difference in the weight, whether you're looking with an L36 or an L67. There's also a difference in the bolt pattern. Now, I put the values at the bottom, and frankly, I don't expect you to remember that. What I do expect you to realize is without tearing the engine apart, having the engine order vibration made me sit down and research where this problem might be before I took it apart. So immediately I'm going, you know what? There may be something wrong with this flex plate causing all this. Once the trans was removed, guys, we realized whoever put the flex plate on, because it wouldn't line up properly, left two of the bolts out. It was clocked incorrectly on the back of the engine. And you could have done all the balance shaft work in the world and still not found that. That is one of the reasons we want to understand frequency, how many times per second, order, force, and direction. Let's take a look at direction as an example now. Now, before you get your hair on fire and go, Adam, I would have found that without this equipment. That's not the point here. The point is this Subaru has a shake in the steering wheel driving down the road. Any of you working on this car and doing a proper front end inspection would have found this. You would have found that it has a loose tie rod end. But take a look at this. If you look at the readings I took of this driving down the road, you'd realize that it has some vibrations from an fore and aft, that's in blue, that's forward and back. In red, it's vertical, up and down shakes. And in green, the important one here is lateral. This is a directional force on the car side to side. Now over here, we may have some pretty high force numbers, I'll explain those in a little bit, of running upwards of about 40 milligravitational forces, or mgs we'll call them. We actually hit 38.5. The thing is, as we look at other unknown rotating components, not the standard tires rotating, engines rotating, prop shafts or drive lines rotating, over here, this car produced some pretty wicked vibrations that, think about this. Wouldn't it make sense if I knew how many times per second a shake happened? If I said, Adam, I've got a shake that's happening 38 times a second, like you see here, or 19 times a second. The key to finding a vibration or a noise is to figure out, when you know how many shakes per second it makes, what on the car at that point in time is spinning at the same rate. So it's kind of a game of, here's the shakes, what's spinning that fast? This guy, perfect. But what we found here is I've got forces far higher than what you see in the normal rotating components. I have forces in green, right here in green. I have forces that are hitting 106 mgs, 86 mgs, 41, 41, 24 at a variety of different times per second. There is no rhythm with the crankshaft rotating. There's no rhythm with the drive lines rotating. There's no rhythm with the tires. So this tells me these massive vibration forces that I'm feeling don't match anything that's rotating on the car. So without lifting the car up in the air, without taking it apart, I have to sit back and go, okay, I've got massive vibrations that are happening in an unknown area. They don't match anything rotating, which means now I have to stop and think. So why would I have massive forces? Well, let's figure out what direction the force is coming from. Because in blue, that would be shakes of the car forward and back. In red are shakes of the car going up and down, but in green, that's lateral. something is banging this car back and forth. Thus, how it led us to a bad tie rod end banging the car back and forth. And by the way, just one thing to remember, depending on the vibration equipment that you have, I'm showing you a Pico example right here. The accelerometer you're looking at here has a relatively strong magnet on it. But one of the reasons that it is marked on the side here, you can see I've got a lot of time on mine. This X with an arrow, this Y with an arrow, and the Z that's kind of corroded out over here is how they measure the directional force. So if you're going to use direction as an indicator of vibration, then you have to make sure that your orientation on the car is designed where X goes forward and aft, Y goes in a vertical direction, and Z goes side to side. Now, there's another thing to pay attention to, and this one was pretty good. This was another eye-opener for me. Actually, I think this just sealed the deal. I've got a 2007 Lexus LS460, which is a rear-wheel drive, relatively high-end Lexus. The customer's complaint, and just hear me out before you wig on this. The customer's complaint is a humming or droning noise that only happens above 90 miles an hour. Now, look, we've heard all the stories out there. Oh, my car only shakes at a buck, 120 miles. There's no way you've got any business taking this car out and driving it this fast. But the customer complains it hums or drones above 90. Well, guys, I took this waveform in California. They all drive faster than that down here anyway. The thing is, how do I approach this? Well, it was easy. The dealer said it needs a rear differential. Guys, a rear differential in an 07 Lexus 460 is an expensive component. So as I'm at the shop and they're telling me this, I'm like, look, I don't want to take the thing out and go 100 mile an hour. Come on, that's ridiculous. Is there any other way we can approach this car? And they go, well, Adam, it'll make the noise right in the shop. Heck, we can put it on jack stands. And if we get up around 90, 100 miles an hour, you'll hear it. You can hear it moan throughout the shop. I'm like, well, let's try it out. So depending on the equipment you have, this equipment has a couple different graphs here. In red is my mile per hour. In blue is my RPM. So as I'm running this thing on the rack or on jack stands, this was jack stands, as we're running it along, I increased the speed right here. And you can see that in blue, as I got to this line right here, I'm at 2,600 RPM. In red, I'm 102 mile an hour. So I have a pretty substantial increase in speed. And from an amplitudinal, from a force standpoint, my force of vibration was flat, 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 nothing, 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 nothing. And by the way, did you catch? I called it a vibration, but the customer didn't say it shaked. The customer said it has a humming or a droning noise, which I know is a vibration also. There's nothing, nothing, nothing. But all of a sudden, as we increase the speed of only the rear tires on this car, by the way, we have a pretty substantial increase in force of vibration. And you can hear this vibration. The trick is, okay, you measured it, you can hear it. Do you see where it's happening? Well, Adam, right here, your humming noise is happening in a tire-oriented order one. Remember, the one is how many shakes per revolution. So if I said it has a tire one order vibration, that means every single rotation of the tire, it produced one shake every revolution. If I said it had a T2 vibration, it would be producing 2 shakes every revolution, a 3, a 4, on and on. But over everything else, the drive lines look perfect. The engine, perfect. The only massive vibration registered by equipment is, Adam, you have a tire one vibration. For some reason, you're producing an immense amount of force. All right. 1 shake every time the tires go around. Now, what's kind of cool about the Pico software, and I'm not just sitting here telling you what software you need to buy and what equipment to buy, but if I take and hover on the T1 here, or the T2, there's a help menu that pops down. And that help menu is freaking accurate, guys. That help menu will come out and say, hey, on a tire one vibration, you are looking at a tire, a wheel, a hub, a rotor or a drum, a drive axle, or a carrier in the differential. Because think about this. Isn't it true that the carrier itself and the axle and the hub and the brake rotor, drum, wheel, and tire all spin at the same rate, which means it's telling me that I have a vibration producing this force once every time the tire goes around. So it could be tire, wheel, drum, rotor, axle into the carrier. Now, come on, let's be logical about this. Driving the car, it hums or the noises, you want to put a rear end in it. But if I've got a tire one vibration, doesn't it make more sense to you to start with the simple? Doesn't it make sense to start with the tire, the wheel, then move to the hub or the drum and rotor? And then if necessary, take a look at that axle and then maybe tear into that differential, because all that was wrong with this car was tires. The rear tires were bad on it. Before you say it, I know someone's thinking this. Hell, you can say it if you want. I'll listen to you. But look, you're saying, Adam, your tires aren't on the road. I know that. I'm sitting on jack stands. Then how are you telling me tires made a humming or droning noise? That's what we call beating or phasing. Hold on to that thought. Let's jump into this. So in order to understand the teasers that I put in front of you right there, we have to understand some basics about noise and vibrations. So we're going to start with a thing called a source, a transfer path, and a responding component. Guys, most of the time, the source of a vibration, the source of a vibration is a rotating component that is out of round or out of balance. Now think about this. The engine is almost always going to rotate at a different frequency, different cycles per second than, say, a driveline. The driveline is going to spin at a different frequency than the wheels and tires. So if we broke it into the three main rotating parts on a car, the three main rotating parts, we could say engine, drivelines, tires, and wheels. Okay. And most of the time, the source of a vibration is going to be one of those components that's out of round or out of balance. Now, if that's true, if it is the source of our vibration, is an out of round or a balance issue, then I'm stating in this next comment, I said, in these cases, guys, that source can be repaired. However, there are other components on the car. The engine is obviously the first one that comes to mind. Guys, engines naturally have vibrations. Part of an engine's natural job is to sit there and vibrate. And some of them, depending on what you're working on and the configuration, some of them can vibrate relatively violently, okay? But the thing is, if my engine is the source of my vibration, but I determined that that source is common to that component, or that component is supposed to produce that vibration, then we can't fix the source of the vibration because it does that naturally, which means instead of fixing the source, we now have to fix the transfer path. Now, when we talk about transfer path, and this should make sense to you guys, a transfer path could be anything that is connected to or touches or insulates those vibrations. And of course, I put a whole list here. I said, guys, a transfer path could be motor mounts, transmission with body mounts, exhaust systems, anything that might transfer that. If it's transmitting a normal source vibration, we have to fix the transfer. But then we move into the last part of this called the responding component. Guys, the responding component is pretty basic. The responding component is what the customer feels. Look, when the customer feels a vibration, heck, when you feel the vibration or you hear the noise, when you feel that, it could be the floor, the seat, the steering wheel, the mirrors, the dash, the instrument cluster, you name it. It could be any of those. The responding component is what we're trying to keep the vibration from getting to. Okay, source, transfer path, responding component. So what type of equipment do we have available to measure this? You know, I've got a lot of pieces of equipment on the screen, and I just want to go over a few of these with you. From a noise, vibration, and harshness standpoint, there are a lot of different choices that are out in the field today. First of all, I'm going to drag you guys back quite a ways into the old Kent Moore EVA and EVA 2 systems. As a General Motors technician back in the 80s, our dealership, it was a huge dealership up in Renton, Washington. Our dealership had an EVA We had an electronic vibration analyzer. Do you know how many technicians in that shop knew how to work it? This isn't a tough call. None of us knew how to work it because it required math, and heck, it required an understanding of what vibration analyzers do. None of us ever used the EVA. We didn't understand it. Well, now we bring out the EVA. We didn't understand the EVA too. Heck, MasterTech back in the Vitronics days, they came out with the MTS 4100 vibration analyzer. Look, here's the deal. It was as simple as the basics that I just told you. You need to have a way to measure the vibration. When you measure the vibration, you measure how many times per second it vibrates, what direction it vibrates in, and how harsh it is hitting the vibration force level. And the real problem with pieces of equipment like the EVA and the EVA 2 and the NVH analyzer from Bosch, well, now it's Bosch, but Vitronics back in the day, is that it didn't have the ability to help you to understand what on that car is vibrating at this rate. We didn't have that. We'll get to that in a second. Underneath these, I have two different types of listening devices. We have, the design of chassis ears. Guys, chassis ears have been around a long, long time. They have the wired versions, they have the wireless versions, they have the Bluetooth versions like this. But the idea is you can put these clamps on the car and listen to the noises and pick up the possible direction of where they're at. Nowadays, we've stepped up because the prices have come substantially down on these pieces of equipment too now. And we have ultrasonic listening devices, which, guys, we are in the process here at CTI of building a class on ultrasonic noise detection. We've already created quite a few case studies on it. We have come up with some brilliant diagnostic routines with this. That's a topic we'll cover a little bit later. But then as we move to the right-hand side, here is where we're at now with a more modern approach to NVH. There are three different NVH pieces of equipment here that are all fantastic if you're interested in getting involved with this. The one that you see right here in the middle is the IVA. That's the Intelligent Vibration Analyzer by Automotive Test Solutions. Guys, this is a standalone 4-channel vibration analyzer that does not need to work in conjunction with Automotive Test Solutions' other equipment like their e-scans and e-scopes, that sort of thing, standalone. It has incredible software. It does a good job of helping you to determine what rotating component is going that speed. On the bottom right here, this is my particular choice. I use the Pico NVH technology system. By the way, just to give you a heads up on Pico's NVH, most of your dealerships today require this in their dealerships. I've done hands-on training at both Chrysler and Mercedes dealers with this equipment, but GM, Chrysler, Mercedes, others are hopping on board. Toyota's now on board to use this for noise, vibration, harshness also. One of the additions to the NVH kit, depending on how you purchase this, and that's something we can talk about at a later date. I'll give you guys my email if you have questions. You can add on optical sensor capabilities also to do in-shop driveline balancing like we used to do with hose clamps back in the day. But you know what? If you're within the sound of my voice and you're serious at all about wanting to learn about NVH, you guys have to get this phone app. You have to. You absolutely have to. That phone app right there, when it originally came out, was only $100. Now, $100 sounds like a lot for a phone app that you buy, but it was only $100 to buy it. And I knew a few guys that bought it, but no one understood it. Then within a few months, it goes up to $400. And about 3 months ago, he dropped the price. You can literally get an incredible NVH complete system for $100. I have it on my cell phone here. I would not dream of not having it because I don't care if you have the IVA from Automotive Test Solutions, you have the Pico kit from Pico, the NVH that you can put in the cell phone app, because your phone has accelerometers in it. You can, and this is what I've found to work the best. You can take a bag of rice, throw it on the dashboard of the car. That's right, rice. All right. On the dashboard of the car, you drop the phone in it, you go drive it, and this will analyze the vibration. It will analyze how many times per second it shakes. It will analyze how harsh it is. It doesn't do the direction, all right? But if you put in all the vehicle information, your wheel and tire size, your differential gear ratio, you can utilize the GPS unit. Get this, the GPS that's already on your phone for vehicle speed. So it knows how fast the car is traveling. Or you can get a little OBD2 connector, plug it in, get RPM and vehicle speed. All right. But even if you get this app and you don't use it for its ability to measure vibration, it has, in my opinion, the absolute best research material and description of vibration orders, how to measure them, how they rate. And I, as much as I love the app, I use it more for the database that's in it than anything else. It's very wicked cool. You should seriously look into it. Like I said, I'll give you my email address later if you have questions, but that's pretty much a no-brainer. Let's go ahead and move on to this. Here's the cool part about having two pieces of equipment. This is a picture off my desktop, or I should say my laptop, of me looking at a car utilizing the Pico NVH setup and the Steelman chassis here. So because they're both PC platforms, I was able to run both on the car at the same time. I was able to measure the direction and the strength of the force in milligauss or gravitational force. I was able to measure that. I was able to link it through the software to, was it a tire 1, a tire 2, a tire 3? Was it engine related? Was it prop shaft? What is spinning at that speed in the vehicle? And then simultaneously, I was able to hook up noise receptacles from a decibel standpoint, and I was able to match the noise that was created at the same time as the vibration that was created and find the location on the car. So what I'm telling you here is, as I go back to these different pieces of equipment, the only thing that holds you back is your imagination. And like I said, guys, I'm limited to an hour here. If you have any questions on how all this equipment works, I'll make sure in the chat room that I get my email address out there for you. As a matter of fact, I'm going to prop that in there right now, just so you guys have that, so you can get a hold of me later. It's takes me a second. I'm a one-handed typer here. So guys, I just put out my email address to everyone. It is in the chat room. That's adamtheautoguy@gmail.com. So anything that you want to learn more that I don't have a chance to get to today, man, just get a hold of me and I'll help you through with that. All right. At any rate, I just noticed that you asked a question about the name of the app. literally the name of the app. I think it's called Vibration. It's called, I could even look it up on my phone. It's, where's my Vibration app? It's called, NVH for Android. So literally noise, vibration, harshness for Android. But at any rate, let's move on from this. We'll get going. So there's something else to this that I think is going to blow your mind. Actually, I know it will, because you've never thought about this. Every one of you has driven a car that had a tire that was out of balance. And I'd be willing to bet that a good majority of you listening may say, Adam, you know what? I can freaking drive a car and tell you if a tire's out of balance. Because if that's you and you're listening to me say, Adam, when a car has a tire that's out of balance, common enough complaint, I usually feel the vibration between 50 and 60 miles an hour. All right, let's just round it 55 miles an hour. But isn't it true? Isn't it true that that vibration, you didn't feel it until you got to 55, 60, 65 miles an hour, right? So the vibration came in, but ain't it weird that when you go past that speed, the vibration diminishes? And you know what? I got one for you. Chew on this. I think the tire was out of balance the whole time. I think it was out of balance at 5 miles an hour. It was out of balance at 60 miles an hour, and it was out of balance at 80 miles an hour. Why is it that you felt it at 60? And better yet, this is what's going to blow your mind. If you take that wheel and tire off that car and bolt it on another car, you don't change the balance of it, you may feel that vibration at a different speed. Another car, that vibration might not be felt until 80 miles an hour, or maybe a little bit slower. Now, how could it be that an out of balance component can be felt in one car at one speed, but at a different speed in another car? Guys, the hippies had it right. I put it on the screen. It's all about the vibrations, man. Actually, Einstein even came out and said, everything in life is a vibration. And you know what? That takes us to a whole nother level. So I have a small video here and I want you to think about this, and I'll kind of dictate as it goes along. I'm going to pause this and I'm going to turn this obnoxious thing down. I don't think you can hear it anyway, but here's what we've got. Most of you guys would recognize this as a tuning fork. Now, this tuning fork is tuned to a natural frequency of 325 hertz. Guys, that's 325 cycles per second is the natural built frequency of this tuning fork. 325 hertz, okay? Now, natural frequency is the point where everything in our world, guys, your body has natural frequency. Heck, the top of your body versus the bottom of your body has different natural frequencies. The desk I'm sitting at, the computer I'm sitting at, the car I drive, everything in our universe, and Einstein said it, has a vibration. And everything in our world has what we call a natural vibration. And therefore, everything in our world, if it has a natural frequency point, also has a point where it oscillates or produces vibrations. Because see, here's the key. If this tuning fork is tuned to 325 cycles per second, that means that this tuning fork sitting here all by itself, it's doing nothing, is vibrating at 325 cycles per second. You can't see it, but it's just sitting there vibrating. The key is, if I can apply a force of frequency that is close to the frequency of its natural vibration, it will cause this to resonate. So by applying a force, by applying a frequency, when it gets to be the same, watch this. Right here on the screen, I've got my cursor over it. Right now, we're supplying a sine wave frequency, or at 274 hertz, all right? I'm going to keep increasing that. All right. Now, when I increased this frequency and I applied this frequency force, when it got to 325 hertz, I'm going to back this up a little bit. When it gets to 325 hertz, all of a sudden that's vibrating. Whoa, 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 because we hit its natural frequency. It's resonating, right? If I go higher, it stopped. Why did it vibrate only at 325? And let's take this back. I'm going to pause this. Why did it not vibrate below 325, not vibrate above 325, but right about 325? Why did it vibrate? It's because we applied a force that equaled its natural frequency. What did I just tell you? Everything in our world has a natural frequency. You apply a vibration with enough force at the same natural frequency as the component or whatever you're looking at, you will get it to vibrate. Now, how do we take the tuning fork and relate that to a car? Well, watch. So let's move next. By the way, if you guys didn't know this, here's a car. So here's what we're going to do. I am going to make that tire out of balance. I have made this tire have a T1 vibration. It's out of balance. Therefore, it should produce 1 shake per revolution, right? 1 shake per revolution. So here we go. We're rolling along. I have an out of balance tire that's producing 1 shake per revolution. Actually, I would ask you guys this question, but I don't want you all chiming in at once. When do you think the customer will actually feel that? When will they feel that vibration? If you were paying attention to me just a minute ago, I believe that that vibration will be felt by the customer when the frequency of that vibration matches the natural frequency of the combination of the suspension components. And then what it'll do is it'll go up the transfer path, in this case, the rack and pinion, to the responding component called the consumer. So watch. So we're going to roll down the road. And I'm going to pause this again. Up at the top, I have got the vehicle speed, I have the wheel speed in revolutions per minute. I have the frequency. So at, guys, 601 RPM, my tire is spinning 10.02 times a second, 10 hertz. But see, all of my suspension in this car, my lower control arm, my drive shaft, my strut, my tower, all of this suspension hooked into my rack right here. As a combination, our entire suspension has a steering resonant frequency or natural addition of frequencies of 12.13 hertz. And if what I told you is correct, is this: if my steering suspension, everything's natural frequency is 12.13, right now my tire is spinning, making one shake every 10 times a second. Okay. Right now, my customer won't feel it. My customer won't feel it because we haven't matched the steering resonance. Now watch, as we speed this up and we got closer to the actual frequency of all the steering components, that is when your customer felt the shake come through. Now, what if manufacturers realized this and started designing suspensions to where instead of designing the suspension to be 12 hertz, all right, instead of designing it to be 12 hertz, what if they designed that suspension, which most of them are doing today, be 20 hertz? Do you realize if the suspension on that car was designed to be naturally resonant at 20 cycles per second, then that tire, even though always out of balance and maybe shaking on the road, would not transmit that frequency of vibration until it got to 20 cycles per second, or maybe 80 miles an hour or 90. But now as you're sitting there, you're like, okay, Adam, you need to give us something useful out of this class. How about useful and free? I think that'll make it even better for you. Free's good, right? So as you're looking at this picture, a little story behind this. I don't know how many of you have tried to find a rattling component in a car. See, I worked early on at a General Motors dealership, and I was a wind leak, water leak, and rattle specialist. And I tell you something, finding a freaking rattle in a car is hard. You know why it's hard to find a rattle in a car? Do you know why it's hard? Because it could be anywhere. It could be in the door panels. It could be a body molding on the outside. It could be a loose screw up under the dash. It could be, guys, where could a rattle in a car come from? Anywhere. And you know what? Here's the funny part. If you're putting two and two together, this is so cool. If you're putting two and two together, then you'd realize, wait a minute. My rattle only shows up when I drive down a certain road. My rattle only shows up when the bass of my stereo hits a particular sound. Well, duh. You will hear the rattle when whatever that piece is mounted to has the natural frequency applied to it. Now, how do you take that for free and make something useful out of this? So I have my picoscope in this case plugged into my computer, and my speaker output for my computer is plugged into the source input for this car for the stereo. Now, if you use the NVH system from Pico, it has a noise generating system. It has a noise generator. Now, check this out. On my cell phone for free, you can go out. The name of mine, because I know you guys are going to ask, the name of mine is, where is that? It is called Frequency Generator. That's right. I have an app on my phone called Frequency Generator. You're going to love this, guys. It's free. You download a frequency generator. What it allows you to do, it allows you to turn your phone on and produce a variable frequency. I can do it in a square wave. I can do it in a sine wave. I can adjust it from anything from 0 all the way up in the spectrum to where you can't even hear it anymore. But here's the cue. I can take my frequency generator in my phone, plug it into the stereo of the car, whether it goes into the source input or Bluetooth, whatever it is. And then out of the speakers of the car, I can run a sound generator rather than the stereo, but an adjustable sound generator. And here's what I do. I take my sound generator and I slowly start applying more and more frequency to it. As I apply frequency, I just sit there in the shop and keep going louder, louder, faster, 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 until I hit the natural frequency of the component that the rattling piece is stuck to. And you just have to try this yourself, because once you do this, you're going to go, holy crap, I can find a rattle in a car without leaving the shop. No more of that laying upside down on the passenger seat while someone's driving you down a windy road. No, because I can use the car stereo to finally get the car to rattle. Or as I go more and more and more and more, I just keep turning it up, up, up. Then I hear the rattling component. Now I just go find it. The Nissan Sentra you're looking at here was a freaking rental car that I got in Pocatello, Idaho, not that it matters, to drive over to Wyoming. I'm driving that car and going down the road, I heard this intermittent rattle. I'm like, it's driving me freaking insane. So because when I got back to get the airplane, I had a couple extra hours to kill. I'm like, you know what? I'm going to find the rattle in this car. I grabbed my stuff out of the trunk. I plugged in my signal generator, plugged into the source, turned it up. The rattle was in the passenger door panel. Right in the parking lot, I go, ding, 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 ding. Turn it up. I hear the rattle. Now, did I take it apart and fix it? No, it's a pile of a rental car. But at least I know where the rattle is. I just turned it in. I'm like, it is the coolest thing. And if you took nothing else out of this class, why wouldn't you at least look at a very, very inexpensive noise vibration app to learn to start playing with, even if all you do is read all the information that's in it's wicked cool? Why wouldn't you at least get a free app for a frequency generator, plug it into a stereo system in a car, and prove what I'm telling you, that you can find rattles like you would find vibrations in the car? Just pretty dang neat, man. Real neat. All right. So coming back down from that, look, orders of vibration, as I tried to explain to you earlier, are how many shakes per revolution that we have. So if I had a first order, you should all be able to sit there listening to me and say, Adam, if I had a first order vibration, it's 1 shake per revolution. If I had a half, it would be 1 shake every other revolution. Second order, third order, whatever. All right. So in this picture right here, this should make sense to you. I make a comment, and this is something I've learned over the years using my NVH kit, that if I have a vibration or noise, let's call it a vibration, that is stronger than 10 mgs in force, it's worth chasing. If I have a vibration that's less than 10 milligravitationals, mgs, if I have one that's less than 10, it's not enough for me to chase. So I want you to take a look at the 3 normal rotating components on this vehicle: tires and wheels, engine, and drive shafts. Rear wheel drive, by the way, because if you're paying attention, on a front wheel drive vehicle, the CV axles goes the same speed as the wheel and tire. So we would count those under tire vibration. At any rate, so we're looking at this. I am driving this vehicle at 70 miles an hour. All right. 70 miles an hour, I'm cruising down the road. The software, this is what's so cool about the IVA from Automotive Test Solutions, the Pico, and the app for your phone. They all have software to figure out at what speed everything is spinning. So what the software is telling me now, think about this. He's saying, Adam, you're doing 70 miles down the road, 70 miles an hour. Right now, your tire, if it has an order 1 vibration, if it's order 1, it would be happening 13 times a second. If it was an order 2 shakes per revolution, you would be happening 26 times a second. 3 would be 39 times a second. But if it's an engine crankshaft 1, it'll be happening 82 times a second. If it's 1.5, 123, if it's 2. So what you realize is the frequency at which these 3 components, tires, engines, and propeller shafts, where normal vibrations come from, this software tells me where they're at. Do you realize that the frequency of tires is not anywhere near the frequency of engine speed, which is nowhere near the frequencies of the prop shaft? That means if I measured the vibration properly, my software will tell me the force of the vibration, and it will put it in the correct category. Do you guys see a force bigger than 10 mgs in my sum, my vectored sums from my accelerometer? Is there anything in this list at 70 miles an hour that is higher than 10 mgs? And I think you can look and say, well, Adam, well, that's micro Gs. Wow, that's not even 1 mg. Well, you got a prop shaft on with 10, 0. So you have all these. None of these are worth looking at on this car. But you get up here, it says, hey, we've got 25 mgs of force happening, get this, at 13 cycles per second. If I have 25 mgs of force happening at 13 times a second, what on this car is spinning at 13 times a second? The software tells me it's my tire 1, which once again, order 1, tire, wheel, rotor or drum, hub, axle shaft, carrier. Notice I didn't say pinion because the pinion goes the same speed as the drive shaft. The carrier, however, goes the same speed as the wheel and tire. That's how it works. Now, to be fair with you guys, to be fair, I've grouped a bunch of different vibrations together. I have tire and wheel. I've been covering that with you. We've got prop shafts. We've got drive lines, U-joints, pinions, carriers. We have all these different things right here, right? We have engine-related vibrations. But we have a thing called other vibrations too. And an other vibration or an unknown vibration is a category where, hey, Adam, we measured a vibration on the car. It's not going the same speed as your tires. It's not going any type of speed of your prop shaft. It's not matching any of these things. We have this vibration that we don't know what it is. When you have a vibration that does not match the rotating speed of anything on the car, now we have to use our brain and look at the direction of the vibration. And then we have to figure out a way of where it came from. I tried to explain to you earlier when I showed you that Lexus. I said that Lexus had a tire 1 vibration and the tires were off the ground. We were sitting on jack stands, all right? I used the term beating or phasing as my description for that. What I'm telling you here is that if you have 2 first order vibrations, I have 1 vibration out of 1 rear tire, I have another vibration out of the other tire. Those will both register as order 1 vibrations, but they can cause an adjacent component, like the differential in this Corvette. They can cause that to produce a third order vibration, which for most consumers, a third order vibration they complain about as a droning or a moaning, almost always mistaken for bearings, almost always. And yet with this equipment and some practice, I can figure out whether it was a bearing or not. Okay. So let's try another little video and see if I can make heads or tails out of this for you. There's a drive line, and wow, check that out. A rock just jumped up and knocked the weight off it. Now, if a rock jumped up and knocked the weight off that drive line, you would have to agree with me that that drive line is now out of balance. And if it's out of balance, it will produce a first order vibration. Out of balance, first order vibration. But if I go back and I build a bad U-joint, it's going to be bad here, okay? So here's a bad U-joint. You see that there's going to be some motion there. That cannot produce an order 1 vibration. An order 1 is 1 shake per revolution. A bad U-joint will shake twice per revolution. So if I drove this and I had 2 shakes per revolution, it can't be a balance issue. You can balance driveline all you want. A bent driveline can't cause it either. It's going to be a U-joint. And then if another part of the U-joint goes bad, it skips the third order vibration, goes straight to 4. Now, it takes some practice to understand this, but as I mentioned in the phone app, guys, in the phone app, they explain all this too. You can read all that. Look, it's just about time to get out of here. I want to cover one more topic with you. And this is something I've been practicing with recently with NVH, and it's a thing that we refer to as time domaining. most of you listening to me out there have had a car that has a suspension squeak or a clunk. You've got a squeak, you've got a clunk, you've got a noise. You realize noises do not travel well through the air. Oh, noises travel through the air, but not real good. Air doesn't propagate a noise very well. It doesn't travel very well. However, noise travels very well through certain materials: aluminum, steel, hollow tubes. Different materials transfer sound at a different rate of speed. A noise starts here, poof, winds up over here. Okay. If you had a suspension clunk, if you had a squeak in a bushing, if you had any type of noise, is there a trick to figure out and pinpoint where the noise came from? And the answer is absolutely. Here's the trick. I take two accelerometers in this case. I have two accelerometers right here, two of them. Let's say I've got a noise that's coming from the right front. I think it might be the control arm. I don't know. I take my two accelerometers. I put one at one end of the control arm. I take the other one. I put it at the other end of the control arm. And I don't look for how harsh the noise is. I look to see who saw it first. This accelerometer right here saw the noise 149, so around 150 microseconds before this, which means this accelerometer is closer to the noise production than this one. And I can literally go tink, 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 zoom in and tell you where the noise is on the car. And that's pretty freaking cool, guys. At least to me it is. Look, guys, it's 1 o'clock. I know most of you people have to get back to work. I'm going to stop my share here and bring us back out onto the screen. Guys, please remember, I did put my email address in the chat room. It's adamtheautoguy@gmail.com. Do not be afraid to get a hold of me. Look, if I don't want to talk to you, I won't. All right. But honestly, if you try to get a hold of me, you don't get a response, do it a couple times. And if you have any questions on the equipment that's shown, I just saw something from the Great Bambino. It says, are you using this to diagnose engine mounts also? Absolutely. I do what I refer to as a noise or vibration delta test, where I take, and I just chew on this. It's like I said, I could talk about this for friggin' hours. I take one accelerometer on one side of the mount, another accelerometer on the other side of the mount. And if the mount is doing its job, the delta of transferred vibration will be large. If I have the same vibration on one side as the other, taking direction and force and everything into it, then my mount's not doing its job. And I have several demonstrations of that when we have more time to get into this topic. So absolutely, I'm using it for motor mounts. That was a great question there. So once again, guys, feel free to get a hold of me. If any of you want to stick around, I'll stick around here because I'm running the meeting. If you wanted to unmute your mic and ask a question, I'll wait till you guys take off. Like I said, I'm not a big rush for me, but otherwise, if something comes up down the road, like I said, just get a hold of me. All right. So Brenda, really appreciate you having me today. This was awesome. It was fun. I hope to see some of these guys at ATE East live in person. That'll be awesome in September. If you're there, at least, even if you're not taking my class, pop in and say hi or do something, you know. So
well, I can tell you there's some people that are on here that already are getting signed up for ATE, so they'll get to see you.
that's awesome. I'm really looking forward. It's gonna be so nice to get back out in the field live again, Brenda. I missed it, man. It's been it's been like a year and a half. I did a live I did a small 40-person live Pico hands-on class in AES Wave down in Fresno for a club that I have down there. It was so nice to get back up in front of people for a couple 4 hours or so. So I am really looking forward to it again. That's going to be great.
And we are too, and we appreciate it, Adam. And thank you again for today. This was an awesome class.
It is. I really wish this is one of those topics I wish we really had the time to do it justice. Like a week. But no, it is really one of those topics though, you know, so yeah.
Right. Okay, well, thank you. I'm going to stop the recording.
Yep, I see that most people are dropping off. I don't see anyone that had anything to ask.